Yeah.
It is a constant enthalpy process.
Yeah.
But for ideal gas, enthalpy is a function of temperature.
Alone.
I think for enthalpy is a function of temperature, so there shouldn't be any temperature drop.
Yeah, that is true, but that is the thing that you get automatically from the general expression. If you do it for a general equation of state, the dt by dp will become 0.
But sir, for your assignment, you have given the number 3 problem. Is that isenthalpy you have told to find del T del P and del T del P.
Yeah, that is for general equation of state.
But you have written for the case of an ideal gas.
Is it specialized in the case of an ideal gas? So once you get the general expression, what is the problem in specializing to the ideal gas? You get the expression for the general equation of state and then calculate the coefficient by using P equal to RT by V. That's all there is. I don't see any contradiction. You might be able to infer certain results automatically by inspection. You get the general result, then specialize to ideal gas. Right? Certain things you can infer because the enthalpy and internal function of temperature alone, you might be able to infer. But certainly that cannot be in contradiction with the general result. The general result is valid for any equation of state. It must be valid for an ideal gas also. Nothing is meaningless for an ideal gas. They are meaningful for an ideal gas also. Turn out some of the coefficients are 0. Right? So the coefficients, that is something that you have to understand. This is an important calculation part of this section of the course is to be, for instance, we took up this one, dP by dV at constant internal energy for a free expansion process. So, there are many ways of proceeding. So you should first think about what could be the shortest way. Right? So here, I would think because we know very well that P is given as a function of E and T. This is the starting point. I would recommend that you think in terms of transformation of variables and the use of the chain rule and the implicit function theorem rather than just start blindly manipulating the differentials and be led nowhere. That you just keep on. In fact, some books even have a method called Jacobian, method of Jacobian. All that I think is really not needed. And in fact, more than complicates the matter rather than. This is the method that you can use anywhere. For any encounter transformation of variables, all this says is when you have transformation of variables, how do the derivatives transform? That's all you have to know. So the two main elements are the chain rule and the implicit or the inverse function theorem. This you can apply to anywhere. The method of Jacobian is some cooked up thing to make it easy for you to get some derivatives maybe. But I don't recommend that, and you won't get any points in the quiz for using those methods. So now I clearly see that for this derivative, P must be equal to the function of P and E. I see that P is already there, but I have T instead of P. So clearly, this is what it would be. And now if I want to write dP by dT at constant E, I can use the chain rule. It would be dP by dT at constant E plus dP by dT at constant E times dP by dT at constant E. And this I know can be obtained from E as a function of E and T that we have already got. Some of the derivatives we have got because those are the most commonly needed. Some derivatives I can cook up which are not really very common, but just to test your ability to arrive at these expressions. So I would rather proceed logically rather than in a blind way, and which sometimes you might get to the right answer in a shorter route, but it might not be very trustworthy. So I know that from here, this is what we are looking at. E expresses a function of E. So this is obtained from an inversion of this, and the inverse function theorem automatically gives you that formula. which is the dE by dV at E negative, and inside would be the inversion condition derivative. For this to happen, dE by dt must not vanish, so I will put this in the denominator. It's very easy to remember, and I will then have the other derivative on top. You can also cancel the dE and look at it as whether the order is correct, but then you have to account for the negative sign, right? So that is not always, those kinds of cancelling of differentials will not always work. The negative sign is very much a part of the formula. You cannot get rid of it. Right? So then you substitute all of this. We know again further, this can be expressed as a function of, this is nothing but CV. Right? So you put all that in, then you have what you want. I'm not going to do it, I'll give the consolidated list of expressions of all the coefficients that are asked for. And you can check yourself whether your answers match with that or not. I'll certainly give that by Thursday. So, are there any questions? There may be different starting points. I'm not going to compel you to choose a particular starting point, but you should try different starting points for the same formula and convince yourself which is the easiest or the shortest one. Maybe you get a feel for how to arrive at the shortest route to getting any coefficient. Now I want to wrap up point of certain things that we missed out in what we covered, and then we move on to the next topic. We arrive at this, we arrive with starting from here. That is E expressed a function of S and B. To a series of Legendre transforms, we arrived at this. We arrived at that, right? Progressively eliminating one variable after another, you can get that. Then we consider the homogeneous state of a single component fluid, right? And then we define the chemical potential as dE by dN, expressed as a function of S, V, and N, and then we show that this mu, which is defined here, is actually equal to G, which is already defined earlier. G is so I may replace this by this, because the two are equal. So now, if I multiply this by the total number of moles, and I get a famous equation. That's why I forgot to mention that. And so we get NdU is equal to minus SdE plus BdE, and then this can be written as minus SdP plus BdP minus N. This is referred to as the Gibbs-Duhem equation. Gibbs-Duhem equation is nothing more than any of these can be regarded as the Gibbs-Duhem equation in my opinion. But often the one that the final step of the Legendre transform that you get here for the pure component, the chemical potential, that is often referred to as the Gibbs-Duhem equation. It's basically for every step we have what is called as a fundamental equation. And this is referred to as general equation by Gibbs. So when we go to A equal to A of dE, then I have, this is the fundamental equation for the substance. So once the fundamental equation is given, I can get other properties using the general equation. So and so on. So when I come to the final step, I have to either dG or d mu, both are valid. So you may regard that this to be the fundamental equation, both, either of them are the same, and this to be the general equation. So the Gibbs-Duhem equation is only the general equation corresponding to the last step in the Legendre transform procedure to arrive at ultimate fundamental equation. That That's how there is to it. But somehow it's given a special importance for reasons we will see shortly. At this stage, it is just one equation just like this. Now this also as a Gibbs-Duhem equation expressed in terms of E, S and B. Right? So you should understand that. So this is what I wanted to say. I missed out. Then we get back to the question of specification. That is very important, especially when we go to multi-phases and multi-components. So right now we are talking only about single component. So single component, we have seen that from the existence of fundamental equations or fundamental quantities such as E, A, H and G, in terms of these independent variables, it is safe to assume that any one of these four sets of variables are sufficient, often it is said, to completely specify the state of the pure component in its homogeneous state. What does that mean? Right? So I take S and B. What it assumes is that I have the corresponding fundamental equation. Right? So when I specify these two variables, let's say a particular quantity, then I go to the fundamental equation, I get the corresponding internal energy, then I go to the general equation and calculate dE. And so on. All other properties, as we have seen, given a fundamental equation, you can calculate everything: temperature, pressure, heat capacities, various other fundamental equations, everything can be calculated. So all properties of a fluid in a homogeneous state can be calculated from the specification of two. Either it can be this, or it can be this, or it can be this, or it can be this. So we have four sets of variables, and I also pointed out a combination such as PB, why it is not commonly chosen. Most cases that also might work, right? But it is generally not chosen because we know that it doesn't work in at least one case. So better to stick to one of these four, then you are safe, right? So now the question arises, what happens when you do not have a homogeneous state, but rather we have a heterogeneous state, which means properties are not uniform throughout the state. Now in this course, and largely in most of the textbooks, a heterogeneous state is the only heterogeneous states we will consider are those which have a collection of homogeneous points, or what Gibbs calls as phases. Heterogeneous means it's not uniform. Now this non-uniformity can take several forms. The most general is, suppose I have a system and let us say, the homogeneous state, everything is same. I have one. In a non-homogeneous, homogeneous, the non-homogeneous, I could have a continuous variation of the various properties. Right? So there is specific entropy and specific point. Certainly you have seen in fluid mechanics the density can change at every point. We have something called rho, which is expressed as a function of the location, and of course time. Here we are considering the equilibrium system, so time doesn't come into the picture. But anyway, at a certain time, we know that there are properties which can change it from point to point in the fluid. Pressure, for instance, you have the gradient of the pressure appearing in the equation of motion. That means pressure can change from point to point, right? So the non-homogeneous state can be very general. In fact, it can have variation from point to point, right? And that specification is really, you have to specify the variable at each and every point. There is infinite number of variables. Let us say now, this is no longer homogeneous, but non-homogeneous with continuous variation. Then I have to specify S and B at every point. There are infinite number of points in the system. There are infinite number of information I have to give at each and every. That is why the homogeneous state is very simple to handle. It's the simplest kind. But in this course, for us heterogeneous would be a finite collection of homogeneous parts. That means it can be, for instance, 2 homogeneous parts, or 3 or 4, but finite. Okay? So what it means is that there is, if you look at the system overall, there is heterogeneity. The properties of this would be different from that of this. For instance, water boiling at 1 atmosphere and 100 degrees centigrade, that is, has liquid and vapor both existing at the same temperature and pressure. Temperature and pressure are the same for both the phases, but we know very well that the specific volume of the vapor would be much different from that of the liquid typically. Could even be orders of magnitude greater, right? So that is one quantity which we know is not equal between the 2 phases. What can you list? Another quantity. Let's take the water, vapor, liquid. Another quantity which are not equal in the 2 phases. Entropy, or more commonly the enthalpy. Entropy also, everything in fact. Now the enthalpy, the enthalpy of vaporization, which is h of the vapor minus h of the liquid, is what we often refer to as a latent heat. So clearly there are these properties that distinguish one phase from another, which is why we call them as 2 separate phases, right? But however, temperature are the same in both the phases. 100 degrees centigrade, 1 atmosphere is the temperature and pressure for the liquid phase as well as for the vapor phase. Temperature and pressure are the same. What else is same? We have to ask, right? So what this means is that now you might argue, since for one homogeneous scale, one homogeneous part, that means C equal to 1 and pi equal to 1, I have 2 variables to specify. You might say that I here, for instance, I will specify S1, V1, S2, V2. So 4 variables, 2 for each phase. It seems very simple to extend it like that. However, there is a problem because the so-called criteria for equilibrium places constraints on these variables. So not all of them can be independently varied. That is important. When I have to specify only 2 variables, I can specify also 3 variables. The minimum is 2, you are saying. So I can say that I will specify 1 more, right? That is totally unnecessary. First of all, they have to be consistent. For instance, I cannot say 25 degrees centigrade, 1 atmosphere for water and give the density of water at 100 degrees centigrade or 90 degrees centigrade. That will be totally inconsistent, right? So when you have to specify 2, we specify only 2. So we will find that in this case, for instance, these 4 variables are not independently variable, and there are constraints based on these variables, right? I will make that appear on the face of it by the so-called criterion for equilibrium, right? So we need to know what is the minimum number of variables that I have to specify when you go to a heterogeneous state. So we are forced to consider the criterion for equilibrium. So far we have not considered those. Those are valid for all systems, homogeneous and non-homogeneous. But for homogeneous, they don't impose any constraints because everything is anyway uniform. But for heterogeneous, certain properties are different, but certain properties we have already seen. P1 is equal to P2 and P1 is equal to P2. Certain properties are the same for both the phases. Those will put constraints which will reduce the number of independent variables to be specified from 4 to a lesser quantity. We have to take into account those constraints in full, right? So for that, we will introduce the Gibbs' criterion for equilibrium. This is an important part. So what I would emphasize in this part is not so much the arguments and the proof of what we are going to arrive at finally, but rather the results are very important. And so first I write down the criterion for equilibrium, which is a bit difficult to understand, then I will explain. So Gibbs listed first two criteria for equilibrium, which I want to write accurately. So first criterion is for the equilibrium of any isolated system it is necessary and sufficient that in all possible variations of the state of the system, which do not alter its energy, the variation of the entropy of each entropy, that is of the system entropy, shall either vanish or be negative. Now the second criterion, I won't write it down. The second criterion is very similar to this, that is, all possible variations of the state of the systems do not alter its entropy is regarded as equivalent statements of the same criterion. The second statement which Gibbs gave and claimed that is equivalent to his first statement, we would have to say replace the energy by entropy, the variation of its energy. By the energy here we mean the internal energy, not any energy, internal energy, it doesn't say explicitly, shall either vanish or be positive. These are referred to, criterion 1 is referred to as the maximum entropy principle. And this is the criterion 2 is referred to as the minimum energy principle. So let's look at the statement. What he is saying effectively, first considering an important equilibrium. What constitutes, what happens at equilibrium? What is the condition that must be satisfied at equilibrium? Exactly defining an equilibrium state effectively, right? Of any isolated system. That's very important to recognize the qualifications that he is giving, right? What do you understand by an isolated system? No transfer of mass, no expansion, and basically what he is defining, the isolated system is one which is enclosed by an adiabatic, rigid, impermeable boundaries or walls. A system which is enclosed by adiabatically, no transfer of heat, right? And impermeable means no matter can come in or go out. And rigid means there is no expansion. Volume of the system remains fixed. The system as a whole, right? So all possible variations of the system which do not alter its energy, but also we have to take into account. Right, so let me look at the first criterion. So I have first two possibilities Gibbs is considering. One is presumably a unique equilibrium state if it exists. Right? So on the one hand, we have an equilibrium state. That's the one that we are interested in. The other hand is all other states that you can consider. But these are not all, it's not unqualified. He says variations in the state of the system which do not alter its energy, which means it has the same energy as the equilibrium state. It's not that, it's actually a constrained optimization problem. So all other states, what is common to both of them? Right? Common to both of them is the energy is the same. The total internal energy of the state, the equilibrium state, must be the same as any state you are comparing with. What we want to do is we are going to compare the entropy, right? But here, even though Gibbs doesn't mention it explicitly, it also means the volume and mole number also are included. When you see him applying the criterion, you will see that it is implied. Right? So, between the equilibrium state and the all other states, the energy is fixed, the volume is fixed, the total volume, and the mole number of the substance. Because we are considering a single component substance only. It can be very easily generalized to mixtures actually. Right? But these are the same. But now what are we going to compare? We are going to compare the entropy, the equilibrium state, and the entropy of any other state. These are, you can consider any state you want, it will be infinite in number. But it's not an arbitrary comparison, but in comparison only we take it among those states which have the same internal energy, same volume and same mole number. So among those states, he says that the entropy, the equilibrium state is such that the entropy, when you vary the state from the equilibrium state, it either vanish or be negative. So that means what he is effectively saying is S minus S equilibrium is less than or equal to 0. Any varied state either has the same entropy as the equilibrium state, or the variation shall either vanish or be negative. So from this arises that among all the states which have the same energy, mole number and volume, equilibrium state is the one which has the maximum entropy. So from that comes the name maximum entropy principle. So among all states of an isolated system, the equilibrium state is the one which has the maximum entropy, subject to this qualification. This is very important. Right? So this is when I'm optimizing f of x, y, I allow both x and y to vary. Right? And then we get one optimum. But I can also fix y and then ask what is the optimum for this fixed y naught. That might be different. Right? We don't know. So this is a constrained optimization. That's a very important part. But what we will take up is the minimum energy criterion rather than the maximum entropy. Right? So the minimum energy criterion says that we have the equilibrium state, because that is the representation we have followed all along. We have expressed E as a function of S, V and N rather than S as a function of E, V and N. It can easily be inverted, but we will follow what we have adopted all along. So this could be, we look at the equilibrium state and all other states, but the entropy, volume and mole number are fixed. Then we ask the internal energy. So Gibbs' criterion says that the internal energy of all other states other than the equilibrium state either equals the internal energy of the equilibrium state or it has to be greater. So which means that among all states of an isolated system which have the same entropy, volume and mole number, the equilibrium state is the one which has the least energy, and that is why we give the name minimum energy principle to that. So it is principle 2 that we will consider. Now, question has been asked in many books that if you considering both are isolated system, the equilibrium state, other state, entropy, volume and Mole number are also fixed, means what can vary between the two states. And because when you consider a varied state, you are saying that the entropy of the varied state should be the same, volume of the varied state should be the same as that of the equilibrium state. Mole number must also be the same. Then what is it that makes the state a varied state? What is it that is different from the equilibrium state and the varied state? The answer to that is also given by Gibbs. What he says is the distribution of the entropy, volume and mole number among the homogeneous parts of the body will differ. So that is how he considers. There is a variational criterion for equilibrium. Properly to solve it, we need ideas from variational calculus, but to simplify everything, what I will do is I consider only two systems, two subsystems rather. So the isolated system is there, and I consider two arbitrary parts within the isolated system. So now for the equilibrium state, so I will call this the prime part, this is the double prime, two parts. Gibbs actually considered many number of parts, right? But I am going to consider as found in most of the textbooks, YBC law or Sandler, you consider two subsystems or two homogeneous parts, right? And I will call at equilibrium, the equilibrium state for this primed part will have an entropy S equilibrium. Volume would be D equilibrium prime, and number of moles would be N equilibrium prime. Double. So there are infinite number of ways in which I can distribute the total entropy, volume and mole number among the homogeneous parts. So I am considering one that would correspond to equilibrium. Now comparison state. So I can talk of the internal energy of that. We see how to compute that. But now I have to compare. To apply this criterion, I have to calculate the internal energy of the difference between the internal energy of the varied state and then the equilibrium state and apply this criterion, right? So now for the varied state, any other state that we may consider, same division, and here I will simply denote could be any other state. Its energy would be E. Now, if I want to calculate E, Gibbs then said the internal energy can be roughly calculated as the sum of the individual parts. So we have two parts now. I take the internal energy of one part and add it to the internal energy of the other part. So he said this would be E to be E prime plus E double prime. Now E prime we know for a homogeneous part, because that is within itself homogeneous, we know that the total internal energy can be expressed as a function of total entropy, volume and mole number, right? E double prime, there is an assumption involved in that also, but I won't touch upon it now. So it seems plausible to write this. Internal energy of the primed part is dependent on the entropy, volume and mole number. The double primed part is dependent on the entropy, volume and mole number of the double primed part. So I add up the two internal energies. Now how many variables really does E depend on? How many variables? 6 on the face of it. But how many actually how many variables? 3 only. Why? They are not independent because what is important to recognize is this is fixed for the total system. So you are going to be given S0, I will call it S0, B0 and A0, and that is the same here. That is how we are going to apply the criterion. The total entropy, the total Boyle numbers of the whole system is fixed. But in between I can distribute in whichever way I want, but I cannot violate the totality constraint. So what this means is that here S prime plus S double prime has to be equal to S0. It cannot be just arbitrary. I cannot say whatever entropy I want. I have S0, I can distribute it in any number of ways, infinite number of ways, right? But the constraints have to be satisfied. And the way we apply Gibbs criterion is that the same S0, B0 and M0 we also figure in the constraints for the equilibrium state. So I have S prime equilibrium and so on to fill in the rest. This is very important, right? So this is the distribution that actually can be different for different states. Now, a common way to apply this criterion is that in fact strictly, even though Gibbs said vanish or negative, we will take this and it's easier. Because I think Gibbs talked about, this is usually referred for stable equilibrium. Whereas we have the partial inequality, not the strict inequality, but the equality also might be referred to as neutral equilibrium. So I will silently remove this from it and consider that the internal energy is the absolute minimum. No other state can have the same internal energy, right? Because often the difference between a stable equilibrium and a neutral equilibrium is given like this is a minimum, right? And if you have a flat, it's often referred to as the neutral equilibrium, standard pictorial representation. So we could have some other states that could also have the same minimum energy as the equilibrium, but we will refer to this. So I don't know, this distinction might not be that important, but I haven't really thought about it enough. But typically modern books use this full inequality. So how are we going to apply that? So first of all, what I will recognize here is that I'm going to now write the internal energy of an arbitrary state and I'm going to expand that around the equilibrium state, like a Taylor series expansion. So I recognize that even though the internal energy of an arbitrary state is as it appears a function of these 6 variables, as pointed out by you, it's really a function of only 3 variables, right? So I can write that as, I can choose any 3 variables, but it has to be either from this set or from this set. I can just explain from here and B double prime from here and N prime from here. Maybe we can do it, but yeah, that I can do. But I cannot choose S prime and S double prime as 2 of the variables, and then some other variable. That I cannot do, right? To make things simpler, because the constraints are among the entropy, among the volumes, and among the moments. So I have to take one. I can take S prime, N, B double prime, and N prime. That is fine. To make it easy and to apply, I will simply choose to express B in terms of all the prime quantities. Because I know the double prime quantities are just given by that constraint. And then to make that explicit, that those act as parameters. So when I, for instance, when I write Z as a function of x and y, then I say that both x and y are variables, right? But sometimes I would have x and y is fixed at some point, b. So then I will say that I'm going to evaluate Z as a function of x, treating the b as a fixed parameter. So it becomes a parameter rather than a variable. Because for my purpose, that those are fixed. So given a fixed set of S0, B0 and N0, I can clearly express the internal energy like that. So the real variables are only 3. Right? So now I am going to write the first order terms in the Taylor series expansion. So clearly that would be the E by ds prime evaluated at equilibrium. Because I'm expanding along the equilibrium state. It means the derivatives all have to be evaluated at a particular point. That is the equilibrium point. Times this. Right? So I look at what is the corresponding equilibrium S prime. Right? So that's what I have. Plus E by dt prime at equilibrium times E prime minus E prime equilibrium plus dE by dN prime equilibrium times N prime minus N prime equilibrium plus higher order terms. This has to be greater than 0 is what we said. Modify it, we make it strict inequality. That means we are giving a stronger condition than Gibbs, that no other state can have the same internal energy as the equilibrium state. Right? So now, the crucial step here is the way I write dE by ds prime. Right? So E is equal to E prime plus E double prime. So dE by ds prime is dE prime by ds prime plus dE double prime by ds prime. Now I can write this as plus dE double prime by ds double prime. E double prime is dependent directly on S double prime, but is also dependent, can be expressed as being dependent on S prime because of this criteria. The S prime and S double prime are not independent. What I will get is S double prime by ds prime. Right? So now what is this derivative? ds double prime by ds prime. Okay, it's there. The answer is there. Is
express as double prime as S0 minus S1.
yeah, E double prime is a function of S double prime takes other variables. S double prime is internal function of S prime. I'm actually using the chain rule here. Minus 1, very clear from this. It's just a sum. So I can write S double prime as S naught minus S prime. ds double prime by ds prime is simply minus 1 because S naught is a fixed quantity. Right? So that's very true. So what I can now write this as dE prime by ds prime minus dE double prime by ds double prime. So if you recall the fundamental equation in terms of the extensive variables, the quantity dE by ds could be associated with the temperature of the system. We consider only homogeneous states then. So I could regard this as given by T prime and this as given by T double prime. Effectively, I am going to replace this by T prime minus T double prime at equilibrium. Temperature of the two homogeneous parts, the difference. This similarly, by using the same arguments, can be probably be written as P double prime, where you have a minus P prime equilibrium. And this would be written as mu prime minus mu double prime at equilibrium. It's greater than 0. So any minimum, if you go back and look at how the derivative condition for f prime of x equals 0, if f of x has a minimum or a maximum at a certain point will come from considering various other values of the function of various other points and then deducing that the first derivative vanishes. So here I will argue, taking the same arguments, the first variation must vanish as a necessary condition for equilibrium. This is the minimum. E must be a minimum. That is implied by this, and without proof, I will then say that the first variation should vanish. That means all the coefficients in the first order expansion, which would mean that this is equal to 0, this is equal to 0, and this is equal to 0. If any minimization problem has a first derivative value, here the three first part 2 derivatives are effectively dE by ds prime, dE by dt prime, and dE by dn prime. Those should vanish. But I have just shown that dE by ds prime is nothing but d prime minus d double prime. This all of them at equilibrium, because I am expanding around the equilibrium state. This was careful consideration. We will run out of time to take this up again tomorrow. This leads to the very important criteria of uniformity of temperature and pressure that we know. We saw that water and vapor boiling at 1 atmosphere and 100 degrees centigrade means liquid and vapor are both at the same temperature and pressure. But I asked what else is the same? Chemical potential is very important. It is the basis for all phase equilibrium calculations. When you go to multiple components, mixture, chemical potential of each one of the components must be the same in all the phases. I consider, of course, two homogeneous parts. It's considered a multitude of homogeneous parts. Clearly, you can consider as many as you want. I can finally conclude the uniformity of temperature, pressure, and chemical potential as a necessary condition for stable equilibrium. We'll take this up in tomorrow's class.